Why is everything going digital? There's got to be some reason, even though analog has the ability to be more precise, right? You understand? Because analog can deal with infinite. Huh? You can't say it's slower than digital. You can't say it's quicker. I mean, we can transmit data analog using gigahertz, right? Billions of cycles per second. I mean, so what advantage does a digital have over analog? You can't say it. Actually, I imagine, I think that's not one of the major advantages of digital over analog. We talked about this the very first of class. Can't say we can transfer more. Everything that comes through this air, by the way, is analog. So your TV stations, your cell phones, that's analog now, because your carriers are analog. No, that's encryption. And I'm receiving your cell phone signals right now. But it's encrypted, right? My phone's ignored them because why? Well, number one, it's not my phone. So you can't say digital's faster, right? Because it's not, right?
Your phone is going there because of carrier. The phone that carries.
So what advantage does digital have over analog? You can't say it's fast. It is not faster. Number one, I can send it further without error. So we're on, what do we use? It would be like me trying to send analog data, would like me getting up on the hill out there, and you're trying to interpret the intensity of a light. Can you interpret the intensity of a light? You can tell if it's kind of bright or kind of dark, but you can't. It makes no sense to you. So the circuits that translates analog are going to be complicated. How far can I get off with a flashlight and you can tell if the dang thing's on or off? As long as you can see me, right? So I can transfer it further without error. So it's more efficient to transmit, right? Without errors. What's another thing we can't do with analog? I can't store analog to use it later. I cannot store analog to use it later, right? We can store digital to use it. So we can transmit it. We can transmit it further without error. Can we transmit it faster? No, right? It's just that it's hard to maintain voltage over distance. As soon as I have a voltage, I have a current, right? You understand? If I have a current, then I have loss in my line. You can do that. How many grounds do you have on your house? You only got one. If you got a meter long enough, go to the measure from the ground at where you're closest to your meter, all the way to the ground to the other side of your house, and you will see a voltage differential, because it's hard to maintain 0 volts over what? Over distance. That's why we have to have grounds all over the place, because if I didn't have grounds over the place, ground would shift all over the place, right? You understand? So we can transmit it over distance more accurately, right, with fewer errors. We can do what? We can store it, because I'm not trying to store a value. I'm just trying to store either a voltage or not a voltage, right? You understand? And the circuits that handle digital are a lot simpler than the circuits that handle analog. So it's simpler, right, for the circuits, right? You understand that. It's what? We can do what? We can store it for later use, and it's what? We can transmit it a lot further distances without error, right? Does that make sense? And that's the advantages, and that's what makes it so big. So the circuits inside this, if this was an analog computer, they would be very complicated, because they're trying to interpret levels instead of just as a voltage. So I can store a voltage, not a precise voltage. I can store a voltage over time. But if I say a battery at 1.5 volts is equal to a 1, as soon as you get your battery home and measure it, it's not going to be 1.5 volts anymore, right? You understand? So it would be hard for me to vary or detect that. So being able to store things for later use, do y'all ever take advantage of that situation? Where? In a car, in your cell phone, you can store what? How many of y'all know all your phone numbers in your contact list? Yeah, so you have and that's ones and zeros. So you're saving ones and zeros inside your phone, right? You understand that? So it gives us the ability to save things for later use. So I can save things, programs. Your programs are sitting out there. How long would they sit out there before you run them? But they're stored as ones and zeros, right? You understand? So we can store it. And then we have other problems too. Well, one of the first things we'll look at. So what we're going to look at is we call them latches and we call them flip flops. These are the memory. These are digital memories. This gives us the ability to do what? Store ones and zeros for what? For later use. Latches and flip flops.
So either way it goes, store memory for later use.
Yeah. Flip flops do a little neat things. They flip flop. But latches just hold out. Either one of them can be used to hold memory. So this is chapter in the book. I thought I already loaded it up, guys. Chapter what? 10.
So you don't have one new time and new Wednesday, correct?
I don't know. I need to look. So one thing I'm going to show y'all right off the bat is, and see if this ever loads, but while it's loading, let me pause here. Flip flops and registers. First thing we'll look at is what we call cross-couple scheme, asynchronous. What does asynchronous mean? Without a clock. Cross-couple NOR and cross-couple NANDs, also called tieback. So this is a latching circuit. This is what we call tieback NORs. Can you see why it's got that name? Yes, no? Because we take the output and do what? Tie back to the inputs. I'm going to bring an input here. I'm going to bring an input here. And I'm going to take this output and tie it back to that input. I'm going to take this output and tie it back to that input.
Is it similar to this, but it wasn't both of them saying tied back to one output and tied
We did the one where we did the open collector, but that was the outputs connected together. Here we're taking the outputs and taking them back into the input. Now we can do the same thing with a NAND gate. So the top one we call it a tieback NOR. It's also called an SR. We'll look at that latch. I think this is the one, if I ever get the trainer to work, I'm pretty sure the trainer uses this circuit right here that these mounts use, I think. We could use either one, but are we okay? Huh? Yeah, these are called, technically these are not flip-flops. These are, when you look at the data sheet, this is going to be called a latch. And you can get these integrated, so we could build them. But you can buy SR latches. You can buy them. They would have them inside a single integrated circuit. So what would happen here? These are NOR gates. NOR gates say what? So what would happen here? No, we got two outputs. Can't say there's. You've got two outputs. One of them's always one of them should be high and one of them should be low. And we'll look at it. And there's some situations we can cause some problems here. Why would this go right here? I'm looking at this one right here. Any high equals a low. All lows equal a high. Really? He likes you. You get him, Jackson?
I have a headache.
One headache.
One headache.
Say that again. At the top, we're gonna do it low.
But wherever I'm putting a 1. Now with this one I'm putting a 0, right? You understand? Does this make sense? Okay. So that's going to cause this output right here to go what? Low, right? Everybody okay? This low is going to couple back through here. I don't have any high, so this output would go high. Right? Are we okay? Makes sense? This would come back up here. As soon as this happened, this would come back here. That would put a 1 right there. Well, it's still okay. Now what's going to happen when this right here goes to a 0? Huh? What's going to happen when that goes back to a 0?
Oh, you it?
Okay, so what I did is I come over here and I started out. I started out with a 1. I started out with a what? A 1 on the top. That caused this output to go low. This one is a low right here. That low is coupled back around here. Here I don't have all lows, right? So any low will give me, all lows will give me a high. This high, and that puts a high right there. Okay. Okay. So this is where we're sitting right here, right? Okay, now I'm going to bring this to a 0. What's going to happen to the output? I've got this high right here.
So it'll stay low?
It'll stay low. This right here, this is going to stay low. This is going to be too low. This right here is going to stay high. So this guy right here is latched. Right? So zeros on both inputs. On both inputs. Is going to equal, this guy's going to latch. It's going to hold whatever last position.
Meaning, it'll still be a 0, right? It'll still be a low.
What do you mean? Yeah, this output will still be a low. This low will still come over here. I have two lows over here. I have lows on both. This stayed a 1 and this stayed a what? Stayed a 0. Okay. So let's leave it like it was. So this was 0 and this right here was a 1, right? Okay, so guys, let's come over here now. And let's bring this right here to a 1. This should go to what? 0. This is going to couple back right here. This is going to go a 0. This is going to go to a 1. Now I bring it back this to a 0 and it stays latched. But now we latch the 1 in the top one. A while ago we latched the 1 in the bottom one. Here we're latching a 1 in the top. So when I put zeros, I say this sucker is latched. It means whatever the outputs were, they're going to stay like that, right? You understand? Okay, you understand? So we started off by what? Putting a 1 right here. If I put 2 zeros, guys, what's going to happen? Well, something's going to happen. One of them is going to latch, but we've lost control of it. One of these gates is going to be faster than the other. Which one's faster? It will latch a 1 or a 1. It's just that we have no control of it. Right? You understand? So I'm going to have to start this thing from a known position. So I'm going to start right here. Okay, so what's going to happen? Any high gives me a what? A low. That puts, this is cross couple. That puts that low right there. I don't have any high over here, right? So this one right here will go high. Okay. Okay, now I can bring this back to what now? A 0, and what happened? It stays latched. It's holding what I put in there last. Now, is this a 1, or are we storing a 1 or a 0? Well, we got 2 outputs. So I'm going to call this output Q, and I'm going to call this output not Q. So it means when Q is a 1, not Q is always going to be a what? 0. Okay. So if I call that Q, what I'm going to do up here is I'm going to call this set. And what I'm going to do down here is I'm going to call this guy here. What do y'all think? Somebody, no. Yeah, there you go. Y'all hear it. Y'all hear Jackson back here. So when a latch is set, it means Q equals to a 1. When a latch is reset, it means Q equals to a 0. And not Q should always be what? Opposite of Q. So latches have 2 outputs. They have one called Q and one called not Q. They always have 2 outputs. Sometimes we don't bring both outputs out of the integrated circuit. So what did I do to set it? I put a 1 right there and I put a 0 right there, and that did what? Q output went to a what? 1, not Q, went to a what? 0. So when I reset it, so I come up here and put this on here. So zeros on both inputs, zeros on both inputs, both, not one of them, both. It means this guy's going to be what? It's going to be latched. Latch means it's going to hold whatever was there. Okay, so let's reset it. When it resets, Q should go to a 0. Okay, so I'm going to come over here, I'm going to put a 1 right there. That causes this guy right here to go to what? 0. That causes this to go over here. That causes this to go to a 1. Then I'm going to bring this back to a 0. What's going to happen? Now Q went to a what? A low, so that means it's reset. But I have it latched. Why is it latched? Because we got zeros on both inputs. That's exactly right. So we have these two inputs, right? You understand? And these are called, and by the way, these are called SR latches. Can you see I got that name? Because of set and reset. So latches and flip-flops will have a Q and a not Q output. When we say it's latched, what does that mean? Huh? When we say it's latched, what would you think latched means? It holds whatever it was, right? You understand? If it was reset, it's going to stay reset. If it was set, it's going to do what? It's going to say set because it is, starts with an L, latched. Sound like Ferris Bueller. You ever saw Ferris Bueller? Well, about economics, something about voodoo economics or something. You finally spell the whole word out to the class. So when it's latched, is it going to be set or is it going to be reset? It's going to hold whatever it was when we latched it. That's why it's called a latch. Latch don't mean set. Latch don't mean reset. Latch means it's going to hold whatever it had when we latched it. That sounds like a good true cause question. Latch means. So we can set it. When we set it, what does it mean? It means the Q output goes to a 1. When we reset it, it means the Q output goes to a 0. What about the not Q? It's going to be opposite of the Q. So we don't say a latch is latched or unlatched relative to the not Q. We say it's latched or set or cleared relative to the not Q. We say it's set or cleared relative to the Q. This guy, to latch it, I got to put what on both inputs? Zeros or lows. I set it or reset it with a 1 on one of these inputs. What happens if I put a 1 on both of them? Well, we call that an invalid state. If we put a 1 on both of them, both outputs go low. And we can't say it's latched, we can't say it's set, and we can't say it's reset because of the Q and the not Q are not opposite of each other, right? And when you take both the ones off, one of these guys it's going to come up either set or cleared, but I've lost control of it, right? By the way, another thing we use for reset is also cleared. Cleared. We say the latch is cleared. So cleared means the Q output is going to go through. Because we do have some latches that have a clear input clip put on it. So we can put the latch into a predefined state. So let's see how this guy right here works. Now remember, ands and ors are exactly opposite of each other. So that means if this guy right here latches with a 0, what do you think we're going to latch it down here with? A 1. And if this guy right here sets and clears with 1s, what do you think this guy's going to do? This is going to set and clear with 0s. So let's figure out. So I'm going to come up here. I'm going to start off. Let's put a 0 right there and a 1 right there. What's this guy going to go to? It takes all highs to equal a high. I do not have all highs right there. I'm sorry. Thank you. I said y'all got to watch out for me. Oops. So here we go. So this guy right here would go to a what? 1. That would come over here. This would what? Give me a cross couple 1. This guy here would go to a 0. That puts a 0 right there. That makes sense? Okay, everybody follow that through? Okay. Not yet. We latch it by bringing both inputs to the same state. Here it says I have to put a 0 on both inputs. So it's not latched yet. No, we got to put, but these are my 2 inputs. Here's my 2 inputs right here. These are my inputs to my circuit. Not the input to the gate. This is the input to my circuit, and this is the output of my circuit, right? You understand that? So when we say we're putting zeros on both inputs, we're not talking about what we're putting in here. We're talking about what we're putting out here. So I know if I put a 0 on this one and a 1 on that one, I know this output right here will go to a what? Right off the bat. It's going to go to a 1, right? Everybody understand that? This 1 is coupled back, right? I'm never going to make these 2 inputs right here. In a minute, I'll show you what. So I put a 1 on this one. I made sure there was what? Opposite of each other. Okay, now what I'm going to do now is I'm going to bring this back to a 1. What's going to happen? Now let's follow this through. Do I still have any 1 up here? Yes, this will still be a 1. That's going to bring that 1 right there. I've got 1 on both inputs. That's 1 and 1. That'll put a low. That'll cross couple and put that low in there.
Okay, look. At the top you got in and high equals low.
No. Yeah, but these are not ands anymore. I mean, I'm sorry. These are not nors anymore. These are what? Ands. This is over here what? We're dealing with all highs equal.
So when you just did, you had a high at the first one, but they give you all high. What my thing is, I'm not understanding how you get the output.
So let's go back to the start.
So let's say that this is the test right here.
Wait. So I'm going to put this, and I'm going to put that.
So if this was on a test, this is how you would do it every time. This how the example the question you would put out right here.
Well, I might say what's required to latch it.
Okay.
What's required to set and clear it. That would be the kind of question. Or I'd say, what would I get out if I put this state on the input, right? So I don't know. Does that make sense?
Yeah.
Okay, so what's going to be the output of the top one? It takes all highs to get a low. Do I have all highs? Okay. So it would do what? I'm sorry, this bottom. We don't know. We know this one. We don't know that one. Why can't I do this one? Because I don't know the state of these 2 inputs, right? Okay, but I do know this one right here. I know I cannot have what out of here.
I mean, you can't have all high.
Okay, so that means the output would do what? It takes all highs to get a what? Low. Do I have all highs here? Okay, so I know now this output would go to a what? High. Now what do I have on the top one? Now I know the top one, so I know the output would do what? Go low. Everybody okay? Everybody okay?
Seems like
Okay, hold on. Go ahead. It depends. So this is called a tie back NOR. This circuit is called a tie back NAND. So here it got the name tie back, right? Because the output ties back into the input of it.
now, from what I'm looking at, it looks like for the high back NOR, the reset and the not Q, or the set and the Q, will always be opposite on the tie back NOR. But on tie back NAND, the set and the Q will be similar.
Well, we don't know which one's the Q. This right here causes things to change, right? You understand?
Mm-hmm.
Okay. So you're right. So, well, it depends. So if I come over here and I call this guy right here the Q, then I would call this the not Q. Then you would, no.
Okay.
And this is what we got to figure out. So what happens is this guy right here, this is set, and this is reset.
So how does it change?
This one sets and clears with ones. This one's going to set and clear with 0. They're just opposite of each other. So over here, if I was going to do a truth table, then I said set equals to a 0. So we'd say set, reset, and then we'd say Q. If I said 0, 1, then Q would go to a 0. If I said 1 to 0, then Q would go to a 1. If I said 0, 0, then Q would go to what? Latch. If I said 1, 1, I would come up here and say invalid. So we lose one of our combinations. Because this is this guy right here. I'm sorry. Now what's going to happen with this guy right here? They're just opposite, right? So let me move the truth table up here so we don't get confused. So my inputs, we call them what? Set and reset. And then we have my output Q. Over here, a 1 to 0. In fact, we could do it this way. 0, 0 equals what? Latch. What do we mean latch? It'll hold whatever's there. If I put a 1, 0, then Q is going to go to 1. If I put a 0, 1, Q will go to a 0. And of course, if I put a 1, 1, and you looked at the truth table, this would be invalid. Now, down here, the truth table is going to be set, reset, set ridge. I was thinking about my initial. This is Q. Now, if I was to put not Q right here, then this right here would be a what? A 0, that would be a 1. Right? Understand that? Because of not Q, it's going to always be what? Opposite of Q. So here 0, 0 is going to be invalid. Zero, 1, Q is going to go to a 1. 1, 0, Q is going to go to a 0. And 1, 1, this guy should do what? Should latch. We're okay? Let's see if this works. So right now we've got not Q01. So right now, this can't be the Q. So this has to be the Q, and this right here has to be the not Q. Because 0 was to set it, and 0 means, set means Q goes to what? Q goes to 1. So I should have corrected that earlier, but that's why we got off of this, because, Brian said they're the same, but they're not the same, right? Okay, so that means if I come over here on this one and put 2 1s, we should expect this thing to do what? Latch. Remember, this guy's cross-coupled right here. So what's going to happen? So when we set it, this guy went 0. That 0 is coming down here. I don't have all zeros right here, right? So the output's going to stay a 1. This one comes up here. I have 2 1s, and this output stays in the 0. And this guy right here is latched. So let's reset it. So I'm going to bring this to a 0. I'm going to leave this to a 1. What would this output right here go to? This output would go to a high. That goes there. This output would go low. That cross couples. Now we got this situation right there. This output goes to a 1. I still don't have all highs here. The output would stay high. I do have all highs right here. The output would stay low. This sucker is what now? Latched.
So if it doesn't latch, that means you continue to change it around, or how does?
If I kept swapping the S and R inputs, the two outputs would just follow. But that would be, I could do that with any logic. The feature of this is being able to do what? Latch it. It's being able to latch it. Now this is memory. I've told my computer to latch that and hold it. Now it's holding that 1. How long would it hold that 1? Till you unlatch or reset it, right? Not unlatch until we change it. It hold it forever or until power fails. So this is like on your computer in there. If power ever failed when you're running your computer, what happens to everything you had running at that time? It's gone, right? You understand? Because you've lost all your latches. All your latches are now weird, that right? You have to reload your operating system back in, right? You understand that? Luckily, our phones are powered all the time. This computer right here is not. If I was to unplug this thing and pop this battery out, and then I put it back on and turn everything that I've got going up here is gone because I've lost all my latches, right? You understand? So my latches on here, my memory, I'm either latching a what? Every bit I'm latching either a what? A 1 or a 0. So think about, now we don't use this, we use another feature. We use a type of memory called dynamic memory, which is weird, but it's basically serving the same function. But think about the number of little latches I have on this computer right here. This computer's got like 8 gigabytes of memory. A byte is what? A byte is 8 bits. How many latches would that be? 64 gigabits of little latches inside that thing, holding the what? So it's not these guys right here. They use this different thing. So if I was to come over here on this guy right here, I didn't hear anything. Well, you start off by setting it in one situation, right? You understand? I could have come up here and just as well understand what I'm saying, yes or no? So I could have come over here a while ago and I could have said, okay, I'm going to start off, I'm going to put a 0 right there, I'm going to put a 1 right there, right? I know this right here goes to a what? High, right? You understand? And then this right here goes to low, right? Okay. Right. So that's cross couple, right? Okay, so what do we want this to do? Well, if I'm going to call this the Q, right? You understand? Yes or no? I know this thing sets and resets with a what? Okay, yeah, you're right, a 1 or a 0. But we're setting and doing what? So 0, Q goes to a 1, 0, Q goes to this. So we're setting and clearing this with what? Zeros. Which one had the 0 on it? This one. So now, this one right here, I'd say this would be the set. This right here would be the what? Reset. Now, if I'd have started off the other way, I would just flop them around, right? You understand? And this would have been the set, and this would have been the Q, right? Does that make sense? Once you do it, now once you buy them, you can't, because once you buy these things in the integrated circuits, one of the inputs are going to be called S, and one of the inputs are going to be called R, and you got no option. But when you set the circuit up on yourself, you determine which one's the set, and that'll give you which one's the what, the Q. So what would happen if I come up here, I'm going to put a pull-up resistor right here. And this is going to go to +5. And I'm going to put a pull-up resistor right here. This goes to +5. And right here I'm going to put a switch. A single pole double throw. And right now that puts me a 0 right here. That put me a 1 right there, right? Everybody understand that? Are we okay? Okay. So if I came over here and put a resistor, right? And I put my voltmeter right there, what's it going to measure? Right there. What's it going to measure? It's going to measure 0. Well, that's what we're doing right here. I'm taking the bottom of this resistor and connecting it to common, right? That means this guy right here is nothing but a series circuit. And it's going to drop all the voltage, right? Because I got common on one side. So that means if I flip this up, that's going to put a 0 right there. It's not going to put a 5. It'll put a 5 down here because this is not connected to ground. So that means there's no current flow here. Well, there actually is one current flow, 1.6 milliamps, right? You understand that? That's how much an input takes, 1.6 milliamps, right? So 1.6 milliamps through there. If I put 5 volts on there, that means I'd have what? 3.7 volts right there. Is that a legal high? Yes, that's plenty of legal high. Minimum legal high is 2.4 volts, right? You understand that? Follow me so far. So this is seen as a high. This right here is seen as a low, which would cause what? Cause this guy right here to go to a what? Takes all highs to get a low. That's going to bring alls like this. It's going to leave that low. Everybody understand? I flip this switch down here. This switch right here bounces 500,000 times. It don't make any difference. Because as soon as that first high goes high, that'll see that as a high. That'll see that as a low. It'll switch around. This will go to 1. Now that sucker can bounce from now to doomsday, and it's not going to do anything because it's what? It's latched. So what did I just do? I debounced the circuit. Because when it goes to a what? When it went to a 1, it's latched. A 0, it changes. 1, it's latched, but it's already latched, right? You understand? So if I can get the schematic for the trainer to come up, and I look at these push buttons right here, what do you think these things are fed through? A tie-back NAND gate. I'm almost sure. Let's see if we can get that to come up. We'll try it now. Maybe the let's try this one. So here's the power supplies. So here's these switches right here. So here's our pull-up resistor. This gives us problems right here. This gave us problems, I think Anthony, where he had a gate was putting a low right here, and none of the other switches worked because it only uses one pull-up resistor for all the switches. Y'all see what I'm talking about? Yes or no? See this one pull-up resistor going to plus 5 volts? It comes over here and connects to one side of the resistor, and the other side of the switch is connected to common. That means we flip what switch up, pull-up resistor gives us a 1, flip it down, then it gives a common. Here's these blue switches. This comes into a what? A tieback NAND, right? Notice this is showing us the power supply for the chip. That's not good. Here's the pull-up resistor on this side. Here's the pull-up resistor on that side. And then these guys right here are going to, once we flip it to the other side, it's going to connect it to ground. The other side would be pulled up high. So over here, when I flip these switches, these guys right here are latched, right? You understand? So they're latched, and that's on the first bounce, they're latched. And then from then on, the switch can bounce how many times? 1,000 times, and it don't make any difference, right? Because it bounces. Now what's happening though is this right here is adding more cost to these switches. Why don't they debounce all these? So when we get into our counters, so we're going to get into counters. Once we get through latches, we're going to get into counters. Counters are going to count anything. So when you come into a counter, you better do what to those devices? You better debounce them. So this computer, when I'm tapping on this keyboard right here, and you bound on those keyboards pretty high. What do you think they're doing? Well, somehow they're debouncing these keys. This is done with programs. These computers are one of the first things we learn how to debounce a key with a software program. Now, the problem with software is that they're limited, right? You understand? When they came out with a TRS-80, after about a year, your keyboard started bouncing on you because it was out of the limits of the programmer when they wrote the software to debounce the keys. And how did you fix that? Well, you had to get they sent you a ROM that you put into your computer to add to the debounce. This guy right here don't care. Software is going to have limitations to it. Like my mouse. So my mouse I got at my house started bouncing on it. And I was working in Excel, which was fun. And then I brought my calculator up and hit the 9 key, and it gave me like 5 nines up there. Because why? Because of the bounce. Now, what did I have to do? Well, I had to throw the mouse away. I should have brought it in, guys. I'll try to remember, bring it in to show y'all what we have problems with bouncing. So software is good, but software, once you get out of the limits of the software, then you can't really do anything, right? This guy right here is hardware. It don't care. It don't care if this switch is 1 day old or 15 years old. It's still going to what? It's still going to work, which is pretty neat. So that's the debounce circuit inside the trainer. So we have two switches that are debounced, and all these we're just using basic logic. You know, when you're using your meter and you're measuring highs and lows and turning on the LEDs, you don't care if it bounced. You couldn't see the bounce anyway, right? You understand that? To you, the LED stays on solid even though it did. It's just like these lights right here. Y'all know these lights right here are completely turning off 120 times a second. But we can't see it. Why? Because our eyes do what? We can't read that fast. So the resilience of our eyes, you know, it takes a little while for our, sort of like a propagation delay, it takes a little while for your eyes to actually respond to that change in light. Anyway, so that's our first flip-flop, guys. You see why it got the name flip-flop, right? Or it's also called a latch. The book calls these registers, which means these are just stored. So these are called SR latches. We can buy them, we can look them up, or we can build them. You'll see them done a lot, built into circuits. And primarily they're used to hold data for later use. So once these guys are latched, how long would that one stay up there? I mean, it would stay up there until we do what? Yeah, until we reset it or set it. It's going, yeah. So any questions? What time does this class get over?
I had pride.
I think. What time does it get over?
11:30.
Huh?
11:30. 11 or 11:30.
Y'all don't know what time the class gets out. Well, that's the actual trainer schematics, guys. Okay, no questions? All right, see y'all Wednesday. I got everybody's test back, right? Like I said, the grades are already up on Blackboard. It bounces on the road. Oh my goodness. This one is. I should use that one. That's such a bounce like crazy.
Hey, remove that on top of it.
What's that?
Move that on the top of it. Was I know those lectures. Was that 8 and did that count as 8 and 9?
Yeah, they were 8.
Okay, so that counted as 8 and 9.
It did pop up for 89.
No, one on popped up.
I don't know. I'll go back and look. And that was another question somebody asked. Oh, I know. Was there anything due this week?
Let me get another grade.